In this example, we're finding the linearization of the function, and they tell you the function. We don't always get the function. They want square root x plus 3, and they're giving us our x sub 0 to be 1, and then they want us to find the linearization, and then we're going to use it to find these square roots. So let's first find the linearization. The equation we're using is f of x is approximately f of x sub 0 plus f prime of x sub 0 times x minus x sub 0. And so we're going to have f of x is approximately, they're giving me x sub 0 is 1. So if I plug 1 into the function, I get square root of 4, which is 2. So f of x, f of 1 is 2, plus f prime at x sub 0. Well, we're going to need to find f prime. So I've got square root of x plus 3. That's going to be 1/2 x plus 3 to the negative 1/2. And then derivative of the inside is just 1. So we've got chain rule, but it doesn't really affect it. And that would give me 1 over 2 square root x plus 3 if we rearrange it and get rid of that negative exponent. And so then if I plug in 1 to this, because we want f prime of 1, that's going to be 1 over 2 square root of 4. Square root of 4 is 2, so we get 1/4 for the derivative there. And then we plug in our x sub 0, so x minus 1, into the equation. And then let's just simplify it as much as we can. So distribute your 1/4. Put your 2 and your 1/4 together, and we're going to get f of x is approximately 1/4 x plus 7/4. So that is my linearization of the function at 1. And now we're going to use it to find the square root of 3.98. So if we look at our original function, square root of x plus 3, what we've done is we've added 0.98 to 3 to get 3.98. So that is implying that our x value is 0.98. And since we don't have a calculator, let's write that as a fraction. That 7/8. That is 2 decimals after, or 2 numbers after the decimal, so that's going to be 98 hundredths. Let's leave it as 100 for now, even though we could reduce it. So if I plug in 98 over 100, which is my x, into this function, I'm going to have approximately 1/4 times 98 hundredths plus 7/4. That is, or let's put equals 98 over 400. And let's get a common denominator. If we multiply this fraction by 100, we're going to have 700 over 400. Add that, we get 798 over 400, and that is the answer. We can reduce that by 2, which would be 399 over 200 is what the square root of 3.98 equals. Let's look at square root of 4.05, the other one. And so we're going to think about what x value are we talking about then. If you look at the original function, in order to get 4.05, you're adding 1.05 to 3 to get 4.05. So here my x is 1.05. In fraction form, that's 1 and 5/100 because there are 2 numbers after the decimal place. If we change that into a improper fraction, we could multiply 1 times 100 and add 5. That's 105/100. You can reduce that if you want. I'm going to go ahead and use that because 100 on the bottom is an easy denominator. So I've got f of 4.05 is approximately 1/4 times 105 hundredths plus 7/4. So that'd be 105 400ths. So if I multiply this by 100 and get a common denominator, that would be 700 over 400. And then if I add those, I get 800, or wait, what am I doing? 805 over 400. And that simplifies down to 161/80ths. Then from there, they asked, is it an overestimate or an underestimate? So if we think about our function, let's look at our graph. We've got a square root function. We know what that looks like. And it's being shifted left 3 units because of our shifting rules from pre-cal. So we're going to shift the square root function 3 units to the left. And we know the square root of 1 is 1, so we can plot that. Square root of 4, 1, 2, 3, 4 is 2. So we're looking at that function there. That's our original function, square root of x plus 3. And what we did was we found the equation of the tangent line at 1. So we made a tangent line here. So if we draw our tangent line at the point 1, and since our tangent line lies above the curve, then all of our answers that we get are on this line and they're all above the true values. And so what we have here is both of these are going to be over estimates of what we would truly get on the curve, because what we just found was on the line.